Hello and welcome to my OCR J277 specification complete paper 1 revision guide, newly updated so that it contains hopefully everything that's on the entire paper 1 syllabus. I'm sure there's something I've forgotten somewhere. You can let me know in the comments, but I'm pretty confident this is a really good revision resource that at least touches on every aspect of paper 1. So we will start at the beginning, Unit 1.1.1, Architecture of the CPU. This is from the J277 official specification guide, and we're going to try and cover everything. The purpose of the CPU. The job of the CPU is to carry out the fetch, decode, execute cycle, sometimes shortened to FDE cycle or even FE cycle if you want to be really short. We have three stages. Fetch. The instruction is moved from memory, your RAM, to the CPU. Decode. The instruction is understood by the CPU. Execute. The instruction is carried out. The process is then repeated. Common CPU components and their function. The control unit, or CU, decodes instructions and sends signals to control how data moves around parts of the CPU and memory to execute those instructions. The arithmetic logic unit, ALU, carries out the calculations and logical decisions. A register is a discrete memory location within the CPU designed to hold temporary data and instructions during the FDE cycle. Cache memory is a small amount of very fast memory built into the CPU. It holds frequently used data and instructions. Next, we have the von Neumann or von Neumann architecture, depending on how you want to pronounce it. The von Neumann architecture is a major development in how we built computers. And the key feature of the von Neumann architecture is that the program itself and the data were both loaded into memory. This makes it a lot easier to change and update programs. The von Neumann architecture needs a control unit, an arithmetic logic unit, buses, registers. It also requires input and output so that the user and the computer can communicate. Lots of registers, everybody loves registers. Just memorize what they do, you'll be fine. Program counter, PC, stores the memory location or address of the next instruction in a program to be executed. The memory address register, MAR. The MAR stores the memory location or address for data that needs to be fetched from memory or stored into memory. Please include both parts of that in your description in the exam. Fetched from memory or stored into memory to make sure you get the marks. Memory Data Register, MDR, stores data that has been fetched from or is waiting to be sent to memory. Accumulator, ACC, stores the results of calculations made by the ALU and the value of inputs and outputs to and from the CPU. We're moving through this at a pace. Let's have a look at Unit 1.1.2, CPU performance. Major factors that influence CPU performance. Clock speed. The CPU works at high speeds governed by the clock chip. The faster the clock, the more instructions that can be completed per second. Cache memory. This is fast memory built into the CPU that holds frequently used data and instructions. It is faster to access than RAM, so having a larger cache provides the CPU with faster access to more data. Number of cores. Modern CPUs often have more than one processing unit built into each chip. Each core can fetch, decode, and execute instructions independently. Having more cores allows more instructions to be processed simultaneously. That was a short unit. Moving on to 1.1.3, Embedded Systems. An embedded system is a computer system that is part of a larger device and has a single or limited range of functions. Embedded systems usually have the following characteristics. Usually on a single chip. Small in size so they can fit into portable devices. Low power, so they can operate effectively from a small power source. Rugged, so they can operate in harsh environments. Low cost, making them suitable for being used in mass-produced low-cost devices such as microwaves. They have dedicated software to complete that single or limited range of tasks. Sometimes we call that firmware. Embedded systems are found everywhere. Here's just a small number of examples. Washing machines, dishwashers, microwaves, televisions, home security systems, industrial assembly lines, industrial robots, light controller, medical image systems, anything like that would be fine. 1.2.1 Primary storage, main memory. The need for primary storage. Data and programs need to be stored in a computer system. Software programs and data are stored for the long term on secondary storage devices, for example, a hard disk drive, an HDD. However, the CPU cannot access a program directly from secondary storage. It needs to be loaded by the operating system into what we call primary storage or main memory, typically our RAM. Once the program or data has been loaded into RAM, it can be accessed by the CPU. Classical comparison, you always get this in the exam, is between RAM and ROM. RAM, random access memory, is volatile. That means memory and data are lost when the power is turned off. ROM, read-only memory, is non-volatile, so the data is retained even when the power is turned off. RAM is used to store the programs and data currently in use. Also stores the part of the OS, the operating system, that are running now. ROM, on the other hand, stores things like our hardware settings, the BIOS, the boot up instructions for the computer. Next, we have virtual memory. This is part of the secondary storage that is used to supplement the main memory when all the available RAM is being used. The programs and data that are currently being used by the CPU remain in RAM. However, data and programs that are in RAM but are not currently being used are moved by the operating system into virtual memory on secondary storage. This frees up space in RAM for new programs and data to be loaded. Please bear in mind, however, that it's much slower to fetch data from virtual memory than from RAM. Unit 1.2.2 Secondary storage. So again, why do we need it? What is secondary storage? Well, primary storage, for example RAM, is volatile, so any data or programs that are stored are lost when there is no power. Secondary storage, for example your hard disk drive or your solid state drive, is needed to store programs and data for a long term or permanently. Remember, all secondary storage is non-volatile. Let's look at some common types of storage. Solid-state storage is based on a technology called flash memory. This includes SD cards, secure digital, memory sticks, and SSDs, solid-state drives. The main advantage from solid-state technology is that it has no moving parts. So you have faster read-write speeds than other secondary storage. It's silent. It's more power efficient, so you get better battery life. It is shock resistant, for example, being dropped, being moved around, and it generates less heat. Solid-state storage is robust, portable, and compact, so it is very suitable for mobile devices. However, it is more expensive per gigabyte than magnetic storage. Magnetic storage nowadays is mostly used on hard disk drives, although some people may use magnetic tape for archiving data for the long term. Magnetic storage tends to be very, very high capacity. You get lots of storage space in a hard disk drive. It is very low cost per gigabyte. It's reliable, but it is slower in terms of read-write speeds than solid-state storage. Magnetic storage is also vulnerable to magnetic fields, and because it has moving parts, those parts will eventually break down, and it's more vulnerable to being dropped or damaged while being moved. Optical storage uses lasers to read and write data from CDs or DVDs or Blu-rays. Optical storage tends to be low cost and easy to transport, and is often used to distribute media like movies, music, and games. However, if you take it out of the case, it's easy to scratch and damage the disk, and it's also much slower than solid state or magnetic storage. In the exam, you'll often be asked to choose the right device for a specific situation. When you're asked to do that, there's some key points you need to think about. Capacity. How much data do you need to store? Speed. How quickly does the data need to be accessed? Portability. Does the device need to move around? Durability. Will the device be exposed to shock, damage, or a hostile environment? Reliability. Does the device need to be used repeatedly over a long period of time without failing? Cost. How much money is needed to store the data? You're thinking about cost per gigabyte. Next, we have Unit 1.2.3, Units. The units of data storage that you need to know about are a bit, simply a 1 or a 0, a nibble, which is 4 bits, a byte, which is 8 bits or 2 nibbles. Then you have a kilobyte, which is 1,000 bytes, a megabyte, which is 1,000 kilobytes, gigabyte, which is 1,000 megabytes, terabyte, which is 1,000 gigabytes, and petabyte, which is 1,000 terabytes. You can also use 1,024 for the units instead of 1,000, but that's much harder to calculate. Better to use 1,000, use the simplification, makes it easy to do any sort of data calculation conversions in the test. How data needs to be converted into a binary format to be processed by a computer? Well, computers use switches to store data, and these switches can be in one of two states, on or off. Because of this, we need to convert all data and instructions into binary, which can represent on and off using the two digits 1 and 0. We need to be able to do different calculations for data capacity requirements, one of which is calculating text file size. The calculation is the bits per character multiplied by the number of characters. So if we had 200 characters in 7-bit ASCII, the calculation would be, well, 7 bits per character, so 7, times the 200 for 200 characters gives us 1,400 bits. If we divide that by 8, we get a more manageable unit of 175 bytes. We also need to be able to calculate image file size. This calculation is the color depth multiplied by the image height multiplied by the image width. So if we had an image that was 100 pixels high and 100 pixels across, and that was in 16-bit color, the calculation would be like this. It's a 16-bit image, but 16 bits is easier to work with if we say, well, 16 bits is the same as 2 bytes. And that gives us a calculation in bytes rather than bits. So it's like one less conversion we need to do at the end. So we're going to say that's 2 bytes times the 100 pixels times the 100 pixels. That gives us a total of 20,000 bytes. Then we divide that by 1,000 to get a more manageable unit, which gives us 20 kilobytes. We might also have to calculate sound file size. And this is the sample rate in hertz multiplied by the duration of the recording in seconds, multiplied by the recording bit depth, multiplied by the number of sound channels. So if we had a 100-second sound clip recorded at 8-bit quality, mono, so one channel, and that's recorded at a sample rate of 44,000 hertz or 44 kilohertz, the calculation would be like this. 44,000 hertz multiplied by the 100 seconds. Again, we're going to say 1 byte instead of 8 bits, multiplied by one channel, mono. We end up with 4,400,000 bytes. We divide that by 1,000, we get 4,400 kilobytes. We can divide that again by 1,000 to get the most manageable unit, which is 4.4 megabytes. Unit 1.2.4, data storage. So quite a lot to go through in this. Some people find these calculations difficult. They're not. They just require a little bit of practice. How do we convert positive denary whole numbers to binary numbers and vice versa. Let's start with converting 75 to binary. To do this, create your little binary table. At the right hand side you've got 1, then 2, then 4, then 8, then 16, 32, 64, 128. What we want to do is repeatedly try to subtract each value from left to right from the actual number we have, in this case 75. So we start with the most significant bit, that's over on the left hand side, and we work our way to the right, which is the least most significant bit. What does that mean? Well, we take 75, which is our number we're trying to convert, and we say, can we perform the calculation 75 minus 128? In other words, does 128, the most significant bit, fit into 75? No, so on our table we mark that as a 0. Then we move along one. Can we perform 75 minus 64? Well, yes, 64 will fit into 75. So we do the subtraction, and we mark a 1 in the table, and that leaves us with 11 left over. We move along one. Can we do 11 minus 32? Well, no, 32 doesn't fit into 11, so we're going to mark that as 0. We move along one. Can we do 11 minus 16? No, so we mark it with a 0. 11 minus 8? We can do that. We mark it as a 1, and that leaves us with a 3. 3 minus 4? No, so we're going to mark that as a 0. 3 minus 2? Yes, mark it as a 1, and thus leaves us with 1 left over. Can we do 1 minus 1? Yes. We mark that as a 1, and now we have nothing left, so we've finished our calculation. And that leaves us with the answer 01001011. Of course, we could do a double check on that, couldn't we? We could say 64 plus 8 plus 2 plus 1. What does that equal? That equals 75. I can double check it and make sure I've got the right answer. Reverse. Let's go from a binary number to a denary number. So we've got the number 1001101. We create our table, we fill in all the values, the ones and the zeros, and we say if there's a 1 in that column, we add that value together. So if you look at that column, we've got 128, there's a 1 there. We can ignore the 64 in the 32 column. We have a 16, we have an 8, we have a 4. We can ignore the 2 because it has a 0, and then we can add the 1 in at the end. So we have 128 plus 16 plus 8 plus 4 plus 1, and that gives us 157. And again, we could try and double check that by reversing the process, if we have time in the exam, to make sure we absolutely have the right answer. How do we add two binary integers together and explain overflow errors which may occur? Binary addition has a simple set of rules that you just have to memorize. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Carry 1 to the next column. And that's because 1 plus 1 is 2, which we can't represent in binary as a 2, but is represented as 1, 0. 1 plus 1 plus 1 is 1 carry 1, because obviously 3 ones gives you 3, which is represented in binary as 1, 1. Note, you cannot just do a binary-denary conversion and then add them up normally. You must show evidence of knowing how to perform binary addition. You have to show your carries. You have to do it in the way that I'm going to show you. You can then do the conversion to double check. That's a great idea. But make sure you show evidence that you know how these rules work. Alright, I've got two numbers, 011011010 plus 011010001. We're going to start with the least most significant bits on the right hand side, and we have 0 plus 1 is 1. Next column, 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 0. Carry 1 to the next column. So you can see we've got the 0 and we've got 1 on the next column. 1 plus 0 is 1. Nice and easy. Move along to the next column. 1 plus 1 is 0. Carry 1 to the next column. 1 plus 1 plus 1 is 1. Carry 1. And then 1 plus 0 is 1. Nice and easy, isn't it? Our final answer is 110100011, and we can always do a double check. That first number is 106. The second number is 105. Add those together, get 211. 211 in binary, we can do a double check. Yeah, that should be 110100011. So we can always do that double check just to make sure we've got the right answer. Let's look at another example. In this one, we have a problem. We've gone along, we've done all the calculations, but we now have an issue. In our final column, the 8th column, we've got 1 plus 1, which we know is 0 carry 1. But that would mean we have to create a 9th column. And that's a problem. All the numbers we're dealing with are limited to 8 bits. We can never have a 9th digit. So if you get a situation like this, ignore the final carry and write your answer down in just 8 bits. 0001010. The carry is lost, which means we have what we call an overflow error. Moving the digits in a binary number left or right is called a binary shift. For example, each time the value is shifted one place to the left, the number is multiplied by 2. So for example, if we have the number 33 in binary, that is 0010001. Put that in our table. Yep, that's 33. We've got a 32, we've got a 1, no problem. But if we shift that one place to the left and add a 0 to the right-hand column just to fill it up, we get 66 because it's 01000010. We have a 64, we have a 2, 66. So you can see, shifting it one place to the left multiplies it by 2. If I shifted it a second place to the left, we'd end up multiplying it by 4, wouldn't we? On the other hand, each time the value is shifted one place to the right, the number is divided by 2. If we have the number 68 in binary, it is 01000100. So 64 and a 4, that's 68. Yeah, no problem. If we then shift everything one place to the right and add 0 to the left-hand column, we get 34. If we were then to shift it one place to the right again, we would get 17. So shifting it 2 places would actually divide it by 4. However, you have to be careful. Shifting the number left when the most significant bit is a 1 means that we're losing a 1 because we're only limited to 8 bits in the exam, which results in an overflow error. We saw that when we did binary addition. The reverse is when we're shifting the number to the right when the least significant bit is a 1, which means we lose a 1, which results in what we call a loss of precision. So in the exam, when you're shifting, they might give you a situation where you're shifting too far to the left and you're losing a 1, in which case you get an overflow error, or you're shifting too far the other way and you're losing a 1 to get a loss of precision. Losing a 0 isn't important. We can lose the zeros, but when you lose a 1, because you've limited to those 8 columns, you're going to get an overflow error or a loss of precision, depending whether you're shifting left or right. How do we convert positive denary whole numbers into 2-digit hexadecimal numbers and vice versa? So hexadecimal is a number system based on base 16. The first digits, 0 to 9, are the same as that we're used to, but then we have some extra symbols. 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So let's start with 45. How do we convert 45 into hexadecimal? Well, we do a division. We divide it by 16, and we get a whole number and a remainder. So 45 divided by 16 is 2 remainder 13. 16 goes into 45 twice, with 13 left over. So with our answer 2 remainder 13, the 2 stays the same in hexadecimal because 0 to 9 digits are the same. The 13, however, has to change into a D because that's how it's represented in hexadecimal. So our final answer is 2D. How do we reverse that? What is 3F in denary? Well, we get a little table like this. We've got our units and we've got our 16s. We convert 3F into denary values. So 3 stays the same, that goes under the 16. F is 15, so we put 15 under the units column. And then we can calculate 3 times 16 plus 15 times 1, or 3 times 16 plus 15. That gives us a total of 63. So our final answer is, what is 3F in denary? It's 63. How do we convert binary integers to their hexadecimal equivalents and vice versa? This is actually quite nice and simple. To convert an 8-bit binary number to hex, split the 8-bit number into two 4-bit numbers, two nibbles. Since each nibble or each 4-bit number can represent up to 16 values, 0 to 15, each nibble can be converted into one hexadecimal number. Just convert each number into its denary value and then convert to hex. Let me give you an example. So we've got 00111010 in hex. We're going to divide that into two nibbles and put it into a simple table. Our table just goes 1, 2, 4, 8. So 0011, we put that into our table. How much is that in total? Well, that's a 2 and a 1, it's a 3. Then we put 1010 into our column. We've got an 8, we've got a 2, so that's a 10. The 3 stays the same, but of course 10 changes to an A because it's hexadecimal. 0 to 9 stay the same, 10 to 15 change into the letters A, B, C, D, E, F. So we end up with 3A. The 3 is the same, so 0011 is 3. 1010 is A, because we have to convert the 10 into an A. 3A is our answer. We can reverse this process to convert from hex to binary. Convert each hex number to denary, convert each denary number into a nibble. So we're going to convert C6 into hexadecimal. Well, C is 12. What is 12 in binary? Well, that's going to be an 8 and a 4, so 1100. 6 stays as 6. 6 in binary is 0110. So our final answer, if we put that together, is 11000110. C6 into binary. Continuing with Unit 1.2.4, let's take a deeper dive into characters. The use of binary codes to represent characters. When any key on a keyboard is pressed, it needs to be converted into a binary number so that it can be processed by the computer and the typed character can appear on screen. When you press a key on a computer keyboard, a code is generated that the computer can convert into a symbol for display or printing. It is clear that it is important that systems agree on the codes being used if the data is to make sense. There are agreed international standards that are used to represent the character set for a computer system. The character set is every character the computer can understand. The most important of these is ASCII, American Standard Code for Information Interchange, a set of codes to represent the main characters used in the English language. 128 values from 0 to 127 were required to do this in binary, so ASCII uses 7 bits to represent each character. So we have some examples here. For example, A is represented in binary by 65. Although ASCII originally used 7 bits, in the exam, all your representations will be 8-bit unless you're told otherwise. It is important to remember that ASCII only represents the standard characters on an English language keyboard. To include non-English characters and mathematical symbols, the extended ASCII set uses the full 8 bits in a byte to represent another 128 characters. This expands the available character set to 256 characters from values 0 to 255, rather than the original ASCII limit of 128. Later, Unicode was developed using 16 bits rather than a single byte, providing the ability to store 2 to the power 16 or 65,536 unique characters. Later developments of Unicode use more bits to represent potentially billions of different characters, including graphical symbols and emojis. To ensure compatibility of all these systems, the original ASCII and extended ASCII character codes are the same within Unicode. They are in fact now a subset of Unicode. Now let's take a look at how images are represented. Images can be made up of blocks called pixels. Pixel just means picture element. A simple image can be made up of black or white blocks. Binary numbers can represent these black and white blocks, for example using 1 for black and 0 for white, or vice versa. So that would require 1 bit per pixel, 1 0 or 1 1 to represent each pixel in an image. Most images are not black and white, however. we need to use more bits per pixel to represent more colors. So if we use 8 bits, 1 byte to represent a pixel, we can have up to 256 colors. If we use 16 bits per pixel, we can have up to 65,536 colors. If we use 24 bits per pixel, we end up with over 16 million colors to choose from. In order to display the image accurately, the computer needs to know exactly how to interpret the numbers. The information about the image is called metadata. Metadata just means data about data, and anytime you store anything, whether it's image, sound, or text, there will be some metadata stored with it so the computer can make sense of all the numbers. For images, metadata includes information such as the number of bits per pixel, the color depth, the size of the image in bits, the resolution in the image in dots per inch, etc., and much, much more. The effect of color depth and resolution on quality and size of an image. The number of bits used to represent the colors is often referred to as the color depth or the bit depth of an image. The more colors we have available, the better the representation of the image. However, the more colors we have, the more data we need to store for each pixel. Higher resolution images have more pixels to store, further increasing the data that we need to save. Reducing the size or resolution of an image will decrease the amount of data needed to store it, but it will also reduce the quality. Now let's take a look at sound. How sound can be sampled and stored in digital form. Sounds are a series of vibrations that continuously vary and can take on any value. This means they are analog. To sample and store in digital form, at a set time interval, the amplitude or the height of the wave is sampled. This is then stored as binary data. The effect of sample rate, duration, and bit depth on size and quality. Starting with sample rate. The sample rate determines the quality of the sound recorded. If we sample at a low rate, then we use few samples, and there is a poor match between the original and the sampled sounds. If we sample at a high rate, then we use a large number of samples, improving the match between the original and sampled sounds. Sample rate is usually measured in hertz. 1 hertz means 1 sample per second. A higher sample rate will result in a higher file size, but will sound closer to the original. The bit depth is the number of bits used to store each sampled value. By increasing the bit depth, we can represent the data for each sample point more accurately and provide a better representation of the original sound. However, the more bits we use to store each data point, the larger the file needed to store the data. The duration of the sample is how many seconds of sound are sampled. If we sample more seconds of sound, then the more data we need to store, so it increases the file size. Next, we have 1.2.5, compression. So why do we need compression? Storing images and sound can lead to large file sizes. This can be a problem for sending data across the internet, or saving data onto devices with limited storage, for example, mobile devices. Compression reduces file sizes. This is to reduce download times, make the best use of bandwidth, and reduce file storage requirements. However, data compression involves trade-offs. We have the quality of the final result and the amount of processing power that is needed to compress and decompress the files. Lossy compression is a way of reducing a file size by removing some of the data. As it is removed, the original cannot be recreated from the compressed file. The lost data is lost permanently. Considerable savings can be made with lossy methods, but the issue of quality has to be recognized. Key points: remove some of the data, can make considerable space savings. Once the data is gone, it cannot be recovered, often used for media, sound, images, videos, things like that. However, for some files, losing any information is simply not possible. Losing some characters or words in a text document would make the document difficult to read. Computer programs wouldn't work if some of the instructions were removed. This is when we need lossless compression. Lossless compression reduces file size in such a way that no data is lost and the original file can be regenerated exactly. Two methods that you might cover as part of your course are dictionary coding and run length encoding, RLE. And here we have a nice little diagram just to represent compression. We have the lossy, we have the lossless compression, and just some key points that you can learn just to help you answer any questions in an exam. Now we shall proceed with Unit 1.3.1, Networks and Topologies. Starting with types of network. A computer network is where two or more computer devices are connected together using cables or wirelessly. The two main types of network that you need to know about are LANs and WANs. LAN is local area network. Covers a small geographic area, e.g. a building or a small group of buildings, like an office, a school, or a university campus. The company that uses the network is responsible for the infrastructure. So when you're asked to describe what a LAN is, you need both of those points to make sure you get all the marks. And then we have the wide area network or WAN. This covers a large geographic area and the infrastructure is provided by a large telecommunications company. Moving on to look at client-server and peer-to-peer network architectures. Client-server is a network where one computer, known as the server, provides data and services for many other computers, known as clients. Peer-to-peer or P2P is a network where all of the computers have equal status. The advantages of the client-server model. Backups can be managed centrally, ensuring that all files are included. User accounts can be managed centrally. Software and security updates can be managed by network managers without the need to update every client computer network individually. Network activity can be monitored centrally. Disadvantages. If the server becomes unavailable for any reason, users will not be able to access their files. Can also be more expensive to set up, as requires more expensive hardware, the server itself, and you might need staff to administer the network. The advantages of peer-to-peer: they're easy to set up as they do not require any expensive or dedicated hardware. On the internet, peer-to-peer architecture is useful for sharing files without the need to store data on a central server. Peer-to-peer networks are also more robust as there is no single point of failure. Disadvantages of peer-to-peer: without a central server, there's no central management or maintenance of a peer-to-peer network. This means that software and security updates have to be carried out individually on each peer device, and each peer needs to be backed up separately. Please do not bake your peers. The next topic is factors that affect the performance of networks. So network performance is concerned with how well data is transmitted through the network. The main factors that influence network performance that we need to know about are bandwidth, number of users, the type of transmission media used, the error rate, and latency. Bandwidth measures how much data can be transferred over a network in a given time. Number of users. The bandwidth of the network is shared between the users of a network. Transmission media. What the data is transmitted through. Data can be carried around networks via cables or wirelessly. Error rate. This is the number of errors that occur during data transmission. Latency. This is the measure of how much time it takes for a packet of data to travel across the network. The hardware needed to connect standalone computers into a local area network, a LAN. We have the NIC, Network Interface Controller or Network Interface Card, use either, enables the computer to be connected to a network. In the old days, this was a dedicated card that you have to plug into your computer. Nowadays, the NIC is usually built into the motherboard, and that's your laptop, your desktop, your mobile phone, your tablet, whatever. Switch. This is the device that connects wired devices together on a local area network. WAP. No, not that WAP. Wireless access point connects wireless devices on a local area network. Router connects different types of networks together. For example, a local area network to a wide area network such as the internet. We also need transmission media. This could be copper cables, used to transmit electrical signals, typically used for Ethernet cables, limited bandwidth. Fiber optic cables. These are made up of thin glass strands or fibers which transmit data as pulses of light, much higher bandwidth than copper. Radio waves use part of the electromagnetic spectrum to connect devices together wirelessly. The Internet as a worldwide collection of computer networks. Some key vocabulary and concepts that we need to know. DNS, the domain name system. This matches each domain name, like google.com, to its matching IP address, 216.58.212.228, etc. Hosting. Websites and other internet services need to be placed on a web server so they can be accessed by client computers. The cloud, a generic term that refers to storage, services, and applications that are accessed via the internet rather than being stored locally on your computer, tablet, or phone. Obviously, you do need to have a reliable internet connection to access cloud applications or cloud storage. However, if you do, they can be cheaper to access, they allow online collaboration, you can let professionals worry about security and data protection and things like that. Web server. This is a dedicated computer on the internet that responds to HTTP and HTTPS requests by returning web pages requested by a client computer. Now we move on to topologies, specifically star and mesh. So we have to know about star topologies. This is where all the nodes are connected to a central point, typically what we call a switch or a hub. And mesh, which is a topology where all the nodes, all the computers are involved in the transmission of a message. Advantages of star topologies. It's fast because each node has its own connection to the center. It's reliable. If a fault occurs in one link, other links are not necessarily affected. And it's scalable. It's easy to add or remove nodes to the network. However, there is a disadvantage with the star topology. If the central switch or hub fails, the whole network goes down. Mesh topology advantages. Having no central switch means there's no single point of failure. The ability to send signals via multiple pathways makes the mesh a very reliable topology. Mesh topology disadvantages, well, fully mesh wired networks would be very expensive to implement. If you think about it, if you have 10 computers all linked together, they would all need their own switch, they'd all need multiple cables, it would be really difficult. So we usually do mesh topologies with wireless technology. 1.3.2 Wired and wireless networks, protocols, and layers. Starting this unit with modes of connection, looking at wired networks. Ethernet is the traditional protocol used to connect devices in a wired local area network. Be careful. We often use Ethernet when we're talking about the cables, but technically these are CAT cables. Ethernet is the protocol used to carry data across the network. It defines how data should be physically transmitted between different devices, using MAC addresses to determine which device the data should be sent to. The advantages of using such a wired connection is that we have a stable connection, it's more secure, we get faster data transfer speed, and the signal quality is usually better than, for example, Wi-Fi. The disadvantages of wired connections. It's more expensive to install, more difficult to add extra devices, and devices can only be used in one location. Moving on to wireless. Wi-Fi is a set of protocols that define how network devices can communicate wirelessly using radio waves. The Wi-Fi protocol determines the frequency band and channel that should be used, data transmission rates, how devices should be authenticated when they attempt to join a network. The advantages of wireless connections, we've got cheap setup costs, less impact on the physical environment as no wiring is needed, we can connect multiple devices without the need for extra hardware, users can move around freely and work in multiple locations, and can handle a large number of users. However, there are disadvantages. Compared to wired connections, wireless tends to have slower data transfer speeds. We've got the bandwidth shared amongst many connected devices, which may be an unpredictable number. The connection is not as stable. The signal is subject to interference from other networks. The signal can be obstructed by walls and floors. And is less secure than the wired network as it is more vulnerable to hacking. Another form of wireless is Bluetooth. This can be used over short distances using ultra-high frequency UHF radio waves. It is very secure and does not require a clear line of sight between two devices. Common uses of Bluetooth are connecting Bluetooth headphones to devices, streaming audio to Bluetooth speakers, and sharing files between mobile devices. Encryption. It is very easy to intercept wireless signals, and so most wireless networks are encrypted. The Wi-Fi network uses a unique encryption key to scramble the data that is sent over the network, so that if it is intercepted by an unauthorized party, it doesn't make any sense and cannot be used. This means when a device wants to connect to a secure wireless network, a Wi-Fi password/network security key needs to be entered. IP addressing and MAC addressing. So every device on a wide area network, a WAN, has a unique Internet Protocol address, IP address. This represents the location of the device on the network. Every time a device connects to the Internet, it is assigned an IP address to use for that session by the Internet Service Provider, the ISP. The version that we've mostly been using is IP version 4, IPv4. This uses a 32-bit number to address each packet of data. The address is broken down into 4 8-bit sections, each of which represents a number between 0 and 255, and each section is separated by a full stop. For example, 194.83.249.5. IP version 4 worked very well for a number of years, but it's only a 32-bit number. That means the maximum number of addresses is 2 to the power 32, which is just over 4.2 billion, which sounds like a lot, but when you think of how many internet-connected devices there are worldwide, that number starts to feel a bit small. So of course we had to upgrade, and that meant we moved to IP version 6. And this uses a 128-bit addressing system, divided into 8 16-bit sections. The addresses are written using hexadecimal, and each group is separated by a colon. So as an example here, I'm not going to read it out, but you can see it uses numbers and letters A, B, C, D, E, F because it's hexadecimal. That gives you 2 to 128 possible addresses, which is trillions upon trillions upon trillions. It's a truly massive number. Now, different from an IP address, we have the MAC address, the Media Access Control Address. And this is a unique number that identifies the actual device that is connected to a local area network. The MAC address is part of the network interface card, the NIC, inside the device, and is assigned when the NIC is manufactured and cannot be changed. Standards. Computer standards are official definitions of rules that exist for different aspects of computing. Hardware and software standards are very important, as they allow different manufacturers to make components and programs that are compatible and will work with each other. Without standards, only hardware and software made by the same company could be used together. It is clear that networks require standards in order to work together conveniently. Now let's take a look at some of the many common protocols that you have to know as part of the syllabus for J277. Starting with an old favorite, Hypertext Transfer Protocol, HTTP. This is the protocol that is used by the World Wide Web. HTTP defines how web browsers, the clients, should request, and web servers should deliver resources such as HTML files. Next, we have HTTPS, Hypertext Transfer Protocol Secure. This ensures web page data is encrypted before being sent out of the browser or the server to ensure the privacy and integrity of the data being exchanged. So for example, logging into an account, checking your bank account online, or buying products and services online. File Transfer Protocol, FTP. This is a protocol used to transfer, upload and download data between a client and a server on a computer network. So if you have to explain or define what a file transfer protocol is, please make sure you do that last part, between a client and a server. That's usually essential in the mark scheme. So an example would be uploading the files for a website to a web server if you're a web administrator. TCP, Transmission Control Protocol. This is a protocol that splits the data from applications into smaller data packets that can then be sent across a network. Each packet is made up of a header and a payload. Internet Protocol, IP, defines how data packets should be sent between networks. An IP header is added to each data packet containing the source and destination IP addresses for that packet. Email protocols. We have SMTP, the Simple Mail Transfer Protocol. This is used to send email from PC to mail server and mail server to mail server. Post Office Protocol, POP. Now on to version 3. This is used by home or office client PCs to retrieve email from a mail server. Please use that word retrieve in the exam. Any mails downloaded to the client via POP are deleted from the server, so you cannot access emails from multiple devices or multiple locations. Internet Message Access Protocol, IMAP. Now onto version 4. This is used by home or office client PCs to retrieve emails from a mail server. So far, very similar to POP. However, the mail is stored on the server until specifically deleted, so it is easy to access the mail from multiple devices or locations. SMTP is used to send email. POP and IMAP are used to retrieve emails. IMAP is more advanced than POP. The concept of layers. In order to simplify the network communication process, the different activities involved in sending data packets are divided into what we call layers. A network layer is a division of network functionality. It covers a specific section of how network communications take place. Basically, each network layer says what tasks that layer needs to do. Each layer is self-contained. One layer is independent of the others. One layer does not need to know about how the other layers work, but can receive input from the layer above and output to the layer below. This allows developers to concentrate on one aspect of network functionality when working on new protocols. So the model that we have to know about is the 4-layer model, sometimes called the TCP/IP stack. We have an application layer, a transport layer, an internet layer, and a network layer. You don't need to know about these in detail, but the idea is these layers are concepts. They're just a set of jobs that need to be done. These are implemented by specific protocols. So for example, the application layer could be HTTP or HTTPS. If you're sending an email, it could be something like SMTP. Whereas if you go down to the network layer, that could be the Ethernet protocol if you're sending data on a wired connection, or it could be a Wi-Fi protocol or a Bluetooth protocol if you're sending things wirelessly. Moving on, we have 1.4.1, Threats to Computer Systems and Networks. Starting with malware. Malware is just short for malicious software. There are lots of different types, including virus, a program that, when executed, replicates itself by modifying other computer programs and inserting its own code. Worm, a program that can replicate itself in order to spread to other computers. Trojan, a program that users are tricked into installing under the pretense that it is legitimate and useful software. Ransomware, malware that encrypts a user's files and demands a ransom payment to decrypt. Spyware, malware that spies on the user. Farming, redirects a user to a fake website. Social engineering is a form of attack that involves tricking people into giving away critical information or access details. Different forms of social engineering include phishing, uses fake emails and websites to trick people into giving away their sensitive data and information. Shouldering, sometimes called shoulder surfing, involves finding out login details, passwords, and PINs by watching people enter them. Pretexting, the criminal invents a scenario to persuade the victim to divulge information they might not do otherwise. Often done by phone, but can be done in person. Brute force attack, when hackers try to crack passwords by using software to automatically try every possible combination of letters, numbers, and characters until the correct password is found. Denial of service, DOS attacks. These are designed to bring down servers or websites by flooding them with superfluous bogus requests, such as repeated attempts to log in. A more advanced form of this is the distributed denial of service, DDoS. These attacks use large numbers of compromised machines, a botnet, that have been infected with malware. Data interception and theft. Data theft can happen as part of different methods known as data interception or passive attacks. For example, packet sniffing. A hacker will intercept data as it's being transmitted across a network, or man-in-the-middle attacks. An attacker will intercept a device's connection to the internet. This is often done by tricking users into signing into a fake Wi-Fi hotspot. SQL injection. Here a hacker tries to insert extra SQL commands into input boxes on web forms and web pages, hoping the server will carry out these commands in error. Following on from that, we have 1.4.2, identifying and preventing vulnerabilities. So some common prevention methods that you need to know about. Penetration testing, or pen testing for short, is used to test a system or network in order to identify vulnerabilities in its security that an attacker could exploit. Anti-malware or antivirus software is designed to detect and remove different types of malicious software. Firewalls are designed to prevent unauthorized access to a network and can be provided by either hardware device or a piece of software. They inspect and filter incoming and outgoing data packets to ensure that they meet the security criteria that have been configured. Again, this is one of the situations where you have to make it clear it's incoming and outgoing data packets. You've got to have both to make sure you get all the marks in the exam. User access levels. Users of a network are often arranged into user groups. Each group has different user access rights that determine what software, hardware, and files they are permitted to access. Passwords. These help to prevent unauthorized access to a network or a computer system. However, they are only effective if they remain secret and they are not easy to crack by brute force attacks. Gradually, these are being enhanced or replaced by using biometric authentication, things like fingerprint readers, facial recognition, etc. Encryption. This means the data cannot be read by unauthorized persons even if they manage to access it. Encrypted data requires the correct key to be used in order to be decrypted. Wi-Fi networks should always use secure encryption. Files on a network or removable storage devices can also be encrypted if needed. And let's not forget about physical security. This is about protecting hardware, software, networks, and data from physical actions that could cause harm. Security measures might include keeping servers in a locked room that can only be accessed by network managers, ensuring that backups are kept off-site in a different secure location. Other forms of physical security might be closed-circuit television cameras, CCTV, it might be locking doors, it might be hiring security guards for buildings. These are all different forms of physical security. Now we've got some tables just going through all the different types of threat and all the different types of prevention method. I'm not going to read all of these out. You can pause, write them down, and study them. But we've got ways to prevent malware, social engineering, and brute force attacks here. Whereas on this slide, we've got DOS attacks, SQL injection, data interception, and theft. Let's keep going. 1.5.1, Operating Systems. Starting with the purpose and the functionality of operating systems. System software is software that sits between the hardware and the application software. System software is commonly comprised of operating systems, utilities, and device drivers. The operating system, or OS, manages the hardware in a computer and provides an environment for applications to run. Operating systems have many functions. The first of these is providing a user interface. This is the means by which a user can interact and exchange information with the computer. There are three different types of user interface that you need to know about. First of all, we have the command line interface, CLI. This is an environment where the computer is controlled by typing text commands using the keyboard. The computer cannot display graphics, only text. CLIs use less system resources than graphical interfaces, but are less intuitive. They're harder to learn, and it's easier to make mistakes. They're suited for power users, but not typical kind of users. Graphical user interfaces, or GUIs, are more modern environments that make use of graphics and animations. GUIs are typically based on the WIMP paradigm, so Windows Icon Menus Pointer. These are easier to use than, say, a command line interface, and they're a lot more attractive, but they do also require more system resources. Another one we need to know about is natural language. This is like your Siri or your Alexa. This uses voice recognition to interact with the user. Another powerful function of an operating system is memory management. This is the organization of memory at a system level. Loads programs into main memory, RAM, so they can run. It gives each program a private memory area so they cannot interfere with one another. The operating system has to remove programs from memory when they close. It also moves programs between RAM and virtual memory. Multitasking. This is an operating system feature that allows multiple programs to run at the same time. The operating system has to divide CPU time between all the open applications, switching rapidly between them. Because your OS can carry out billions of instructions per second, it can swap between all these applications so rapidly that they appear to be running simultaneously. User management. The operating system has to manage the accounts of different users, including authenticating users and controlling permissions. File management. The operating system manages the different documents and executable programs stored on secondary storage. Peripheral management. The operating system must be able to manage external hardware devices. This is done through device drivers, software provided by manufacturers that communicates with the operating system and peripheral devices. 1.5.2 Utility software. Utilities are small programs that perform specific maintenance tasks. There are lots of different types of utility, but three are particularly important. Defragmentation software physically organizes the files on a storage device into the smallest number of fragments to improve performance. Encryption software that encrypts and decrypts files on secondary storage or data packets over a network to prevent unauthorized access. Compression software enables data to be compressed into a smaller file to save bandwidth in transmission over a network or storage space locally. And we're almost finished now. 1.6.1 Ethical, Legal, Cultural, and Environmental Impact. Starting with legislation relevant to computer science. The Data Protection Act of 2018 sets out 7 key principles that should be central to processing personal data. These are lawfulness, fairness, and transparency, purpose limitation, data minimization, accuracy, storage limitation, security, and accountability. The Computer Misuse Act of 1990, this act makes it a criminal offense to access or modify computer material and includes hacking and the distribution of malware. The Copyrights, Design and Patents Act of 1988 protects the intellectual property of an individual or organization, making it illegal to copy, modify, or distribute software or other intellectual property such as music and video. We also need to know about software licensing. First up, we have proprietary software. This means the source code is kept secure and is not included when you buy the program. This can stop people changing the code or stealing a company's intellectual property, sometimes called commercial software or closed source software. The opposite of this is open source software. This means the source code for the program is made available so that people can edit and distribute the code as they see fit. And now the impacts of digital technology on a wider society. Just a few issues you need to be thinking about. Ethical issues. Ethics refer to what is right and wrong and how people should behave. The ethical use of computer technology is about acting in a responsible way and ensuring that no harm is caused to others. Legal issues. The widespread use of computers has had a legal impact and new laws have had to be constructed. Computers are associated with a wide range of existing and new criminal activities. Cultural issues. The use of computers has had a widespread impact on culture and society, and it is now almost impossible to imagine life without them. In particular, they've had a huge impact on social interaction and how we access information, education, and entertainment. Environmental issues. Computer technology has had both a positive and negative effect on the environment. For example, while computer devices may contain toxic materials that could be dangerous to human health if not disposed of properly, the ability to work from home reduces the need to travel and could reduce the amount of CO2 produced. Privacy issues. Using computers raises concerns about individual rights of privacy. For example, mobile phone companies can track their customers' location, or websites can track your internet activities for the use by targeted advertising. For Unit 1.6, you really need to pay attention to current events connected to computing so that you can write at length about a variety of topics. This unit is often where you get the longer essay-style questions from in Paper 1, and there's no way we can teach you every single issue that's involved in this. But if you go online, if you watch at YouTube videos, you go to different news channels, you look at current events, you should be aware of issues that might be useful. So, for example, the use of AI, things like ChatGPT and things like that. That's a really good topic to get into just now, because that means you have a lot of information that you can write about if that were to come up in an exam. Okay, that's it. That is everything that I can think of that you might need to know in Paper 1. Obviously, there's some topics that you might need to go in more detail in. I need to keep the video within reasonable time limits, but I hope that was really useful for you in your studies. Now I'm going to go off and start working on the Paper 2 video. Good luck, everyone. See you next time.